If we're only concerned about the very immediate surrounding, which is just what is the cell that I'm in, it compares very, very favorably. And the reason for that is for H3, we really just need to do this effectively constant time, what we call in computer science operation of finding at this resolution, what cell am I in? And then we just look that up in a database. Let's say we use a database that maps from keys to values. So it maps from a hexagon key to a value.
Welcome to another episode of the Mapscaping podcast. My name is Daniel and this is a podcast for the geospatial community. My guest on the show today is Isaac Brodsky, and he's here today to talk to us about H3. So this is Uber's hexagonal spatial index. Without further ado, let's dive into the conversation. Just as a quick reminder, if you're not subscribed, consider subscribing, and all the show notes will be available at mapscaping.com. Okay, let's go. Welcome to the podcast, Isaac. You are the co-founder of a company called Unfolded, and you are the current project lead on something called the H3 grid system. So we're going to talk a little bit about the grid system first, and then I want to sort of bring it back and try and relate it back to what you're doing with Unfolded. But before we get into all that, perhaps you could just take the time to introduce yourself to the audience and tell us how you became involved with the H3 grid system.
Well, thanks for having me, Daniel. My background is really in computer science and software engineering. So that's what I got a degree in. And prior to starting Unfolded, I was at Uber as a software engineer. And I was in a part of Uber called Marketplace. And I kind of think of Marketplace as like the heart of Uber because it's handling matching riders and drivers. It's handling dynamic pricing, aka surge pricing. It's handling dynamic guidance to Uber's driver partners and so on, and all the things that kind of affect what we called marketplace dynamics or supply and demand. And what you can imagine is in order to do all of those things, especially like dynamic pricing, we need to have a very good idea of what's going on in the markets that Uber is serving. And for that, we need to have data on what's going on in those markets. And that's the part that I was really focusing on at Uber. So for those who are kind of familiar with Elasticsearch, I was running some very large Elasticsearch clusters and was providing a lot of geospatial data. And that's how I came into contact with the H3 project. Uber had this need for spatial information in order to do dynamic pricing. And for various reasons, we decided to build this H3 project. And so I was kind of leading it from the data side initially, and then more from the publishing and an open source side.
So we've mentioned this a couple of times already. It's a grid system. So I think we should start there. So is this a spatial index? Is it a coordinate system? Like what kind of grid system is it?
So the academic term for what H3 is a discrete global grid system. And the way I break that down is it's a discrete system. So we're breaking up the world into discrete cells. So every position on the world has a cell identifier associated with it. It's global, which means that it's fully global. So no matter if you're at the North Pole or the South Pole or the anti-meridian in the middle of the Pacific Ocean or somewhere in Texas, doesn't matter where you are, it's going to cover you. And then it's a system of grids. And what this means is not only is it a single resolution grid at a certain resolution where our cells are a certain size, but it's a system of them. So we have in fact, we have 16 resolutions of grid, and these resolutions of the grids relate to each other. So, for example, the resolution 10 grid is created by subdividing the resolution 9 grid in the H3 system.
Okay, so this makes perfect sense. We've seen these kinds of grids before. I think if you think about a raster tile cache, for example, it's a little bit similar, right? So we have parent grids or parent tiles, I guess, and each parent tile is made up of children tiles. So there's a relationship between the two. One of the really interesting things about the H3 system is that it's not squares. So it's hexagons. Could you talk a little bit about that? Why did you choose hexagons?
Yeah, so hexagons are something that tend to throw people when we say that it's a hierarchical grid and then it's hexagons. Because if you try to draw this out, that H3, we subdivide each cell into 7 smaller cells. And if you try to draw that out, you're going to realize it doesn't fit quite right. And we had to make some compromises to actually get that to work. So why did we do that then? Because it causes us to make these trade-offs, and there's some kind of odd edge cases with it. So that's a fantastic question of why hexagons. And I think the thing that it really comes down to is we need a shape which we can tile over effectively the entire Earth. There are actually some pentagons in the H3 system, but we kind of put them in out of the way places where we hopefully won't deal with them. So we need a shape that we can tile over the Earth, and we also need to be able to model things moving around in the real world, and that's the key use case that we had at Uber for it. And hexagons have this very, very nice property that all of the neighbors of the hexagons are the same distance apart. You think for squares, there are 4 neighbors that share an edge with that square, but then there are 4 neighbors that are sharing only a point with that square. And those neighbors have a different distance center to center from that original square that you're thinking of. With hexagons, all of the neighbors are the same distance apart, and this makes it much more convenient to run a variety of different algorithms and modeling on top of the grid.
So when you're saying that all of the neighbors are the same distance away from the center, is this what we sometimes refer to as uniform adjacency?
I believe that's the case. I'm drawing a little bit of a blank on if that's the correct term for it, but I believe that that's the case. It sounds about right. It's certainly the case that you're able to model all of these neighbors as being roughly the same. There is a little bit of variation in terms of like the size. From neighbor to neighbor, this generally doesn't vary, in my experience, significantly enough that you'd be concerned about it. So yes, you can think of it as being a generally very uniform grid.
Okay, and of course the elephant in the room, and this is the first thing people said to me when I said, hey, I'm going to be talking to Isaac and we're going to be talking about the H3 grid system. They were like, what about the problem with the hexagons, Like we cannot build a big hexagon out of these small hexagons. So there's a margin of error there, and I'm assuming that there's just some sort of calculations that happen in the background that account for this.
Yeah, so we can't solve it perfectly. That's the bottom line there. But we can make it a lot harder to run into cases that you don't want with those hexagons. So the first thing is when you're converting let's say a point or a polygon or any kind of shape to the H3 grid so that you can work with it inside of the grid system, you're giving H3 both those coordinates for that point and also a resolution. And what we call that an indexing operation. And that indexing operation is exact at that resolution. So if I tell it I want to index this point at resolution 8, it's going to give me the cell that exactly contains that at resolution 8 inside of H3. It's not going to be affected by any of this distortion. The difficulty happens when you want to move between different resolutions of the H3 grid. Because the way H3 subdivides cells, we slightly offset them from one resolution to another. And this causes a kind of zigzag or jagged pattern around the edge of cells when you subdivide them. So when moving between a resolution to another one, let's say you truncate the precision of that resolution 8 cell that we got to resolution 7, in that case, there is a bit of the cell area which is in error if you try to render that cell out. It's about, I believe, about 7 to 8% of the area is in error is what I calculated out. So it's possible to say, well, my analysis is okay with this, and just kind of continue from there and just say, well, I can truncate the precision of this and be okay because maybe I got my data from GPS and I'm not that certain of where exactly this point was. But for some use cases where you do want to preserve those exact boundaries in the cells, you have to be a little bit more careful to ensure that you don't render the data at a different resolution than what you originally indexed it at. So for example, maybe you truncate precision of the index in order to save space when you're storing the data in a database, but then when you're rendering it out, you use that original resolution that you used.
The way I think about this anyway is that there's a certain amount of smoothing that happens, because if I take my discrete data, if I have a point layer, if I have a polygon layer, and I push it into this grid system, it's going to be sort of smoothed out. It's not going to preserve those original boundaries anyway. I'm not saying this is an excuse and it makes everything okay, but I think that this probably is designed for quite specific use cases and not for every use case.
Well, it's certainly true that it has that effect, and we were very influenced by this use case of receiving like GPS locations or locations from navigation satellites, anyways. And for those, you certainly have enough error that this kind of smoothing operation is usually beneficial to you because you have uncertainty as to where the data point actually occurred. When you have a great deal of certainty and you really need to be preserving boundaries, and you're trying to use this as a spatial index, in that case, that can be more of a case where you want to choose a discrete global grid system that has this kind of exact containment property that H3 doesn't have.
Yeah, and that makes perfect sense to me. I would like, I think it'd be great now if you could just walk us through a really concrete example of what this looks like. Okay, so let's say I have a building layer, a polygon building layer for all of the buildings in Denmark, and I really want to use the H3 system. Could you walk me through what the process looks like, or even if that makes sense to do this with the H3 system?
It can certainly make sense. It does take a little bit more of what is the use case. So maybe we can expand this a little bit and say you want to calculate, let's say, the density of buildings or the number of buildings in an area. And for something like that, it's something where we can very easily compute a kind of metric that we can associate with an H3 cell. Projecting the buildings into H3 on its own, we're kind of left wondering, what are we going to do with it? So let's just attach a metric here and say that we're going to count the number of buildings in different areas. And so what we'd expect to see from that is like urban areas are going to be higher values, and then probably more rural areas are going to be lower values. Using H3 for this, what we're going to start out with is, of course, the input data, which is the polygons and any information that's associated with those buildings. From there, H3 has these functions that we can use to convert from this data in, let's say, point or polygon form into the H3 grid. The way you use these functions is we have bindings to different programming languages and to different databases. It's a little bit of a do-it-yourself endeavor right at the moment. So if you know Python or R or Java, one of those programming languages, or if you're using Postgres, Elasticsearch, some other databases, you're able to do it within those environments. From there, for the polygon example, we're going to select a function in H3 called Polyfill. And what this does is it takes an input polygon and it finds the H3 indexes which cover it. Polyfill has a little bit of an odd history in terms of how it was built. It makes some assumptions that you want to have exclusive coverage. In this case, it doesn't sound like we really do want to have that. So we might index at a little bit higher resolution than we would normally. So we would run polyfill on our input data, maybe choose a little bit higher resolution. And then we have a list of indexes for every single building. At that point, what we can do is we can use kind of our usual off-the-shelf data processing tools. And this is one of the great things about H3 is we can just take these data processing tools that we would use for other kinds of data and apply them to geospatial data. And this scales really, really well. So if we wanted to use pandas in Python for this, we can do that. If we wanted to use Spark, we can use that. If we want to use any kind of off-the-shelf database, we're able to use that because they're able to treat these H3 identifiers as just strings or integers and work with them very, very efficiently. Let's say at that point we want to put it into one of these data processing systems or database systems and maybe group by the H3 identifier. At that point, we have an H3 identifier and we've grouped by it. So we have some aggregation over that H3 identifier, which is maybe the number of buildings in it. When we have that, we have essentially a data source that we can use for analytics that is built using the H3 system, because we have mapping from H3 identifier to a metric value for that cell. And from there, we can, of course, do database lookups. We can very quickly say, I'm in this area. I want to know how many buildings there are around me. That is just a matter of checking where am I, finding the H3 identifier, and then looking it up in a database which is set up to map from H3 identifier to that metric value. But we can also do things like visualize it. We can send it to a visualization tool such as Kepler GL or DECGL that are able to understand H3 identifiers, and we can create a heat map of where are buildings in Denmark, and that's happening without converting the data between different formats. So we're able to do all these different things: analytics and modeling, lookup and search, and kind of these spatial indexing functions, and visualization, all with the data being kept in the same format.
So that sounds absolutely brilliant, and I'm glad you walked us slowly through the whole system so people like me could follow along, and all the way to the conclusion where this data was being consumed by a client. So that was fantastic. Thank you very much for that. It sounded like, so we have the H3 identifier, and to that identifier we can attach a value. So before we were talking about a building layer, so we could have whatever value from that building layer attached there. Can I attach multiple values to that, or could I somehow link back to the original geometry?
So in terms of attaching multiple values to it, that's something that H3 doesn't really have an opinion on. H3 kind of comes from this, I would say, a little bit more of a computer science background, where it's a tool fairly specific to, I have a point and I want to find a cell identifier, or I have a cell identifier and I want to truncate it, and these kind of operations within the grid. But what H3 is working with is either just points or these cell identifiers. And so it doesn't really know what you put next to it inside of your database. So you could create a database in a big data system where one of those columns is an H3 identifier, and those other columns can be really whatever you want within the constraints of that database. So if you want to attach categorical metrics to it, if you want to attach numerical metrics to it, if you want to attach even original geometries, which might be a little bit expensive, but is certainly possible, especially for points, that's very possible. H3 doesn't really have a constraint on it, because what H3 is handling is really that single column, which is the spatial identifier, and which you're probably using as like a primary key for that table. But in terms of what you do with the rest of that table, that's really up to you, and you're really able to very freely choose what you want to associate to that identifier.
How does this is a very sort of loose question, and I apologize for that, but I'm hoping you can give me an idea of how this compares to speed of say, like a normal sort of radius lookup, a point and polygon lookup. What is near me?
So that's a fantastic question, because this really gets into the use of H3 as a spatial index. If we're only concerned about the very immediate surrounding, which is just what is the cell that I'm in, it compares very, very favorably. And the reason for that is, for H3, we really just need to do this effectively constant time, what we call in computer science operation, of finding at this resolution what cell am I in. And then we just look that up in a database. Let's say we use a database that maps from keys to values. So it maps from a hexagon key to a value. So for that operation, that lookup operation is also generally going to be roughly constant time, let's assume. But if we wanted to do a neighborhood lookup, we might have to scan a large number of different points and compute their distance from where I am now to where those points are. I answered a little bit more of a narrow version of that, which is for a single cell. But of course, maybe I want to find things that are within a certain radius of me. And H3 is actually, very interested in this radius question. This is, as we mentioned before about the equidistant neighbors, this is a very important property in the H3 grid, that we are able to find these rings around an origin, and these rings approximate a circle kind of as best we're able to. For that, we're able to generate, let's say, all of the cells that are within a 2 grid distance from you, and then we can do the lookups on those. And so this does increase the complexity, a little bit more because we need to look up these different cells that are near you. We're able to again take advantage of the spatial indexing property of finding nearby cells, and we're able to take advantage of this hexagon property, which is that finding nearby cells approximates a circle.
Thank you very much for the clarification there. Really appreciate it. This might seem like a bit of a silly question. So up until now, we've been talking about transforming discrete data into this grid, putting it in the grid. Is the same thing possible with image data, with raster data?
It certainly is possible. In fact, I just saw an example that somebody has shared to me about placing elevation data into the H3 grid. And you can imagine that what we talked about with polygons earlier, similar processes can be used for really a very wide range of data. So you can think about, maybe I have like GPS traces. This is kind of one of the use cases I come back to very frequently as an example. We're able to find for each point of those, find the associated cell, and then in some way project that trace into the H3 grid. And you can imagine for a raster, we can also think about different ways of getting that into the H3 grid. We could do that in a few different ways. One is by sampling from the raster. So we take an H3 grid, we find a bunch of points that we want to sample from the raster, and then we use that to move that raster data into the grid. We could also do it in another way, which is take all the pixels in that raster and find the associated H3 cell and move the data in that way. So there are different ways of getting data into the H3 grid system.
So it sounds really flexible in terms of the kind of data we can put in it and the kind of things we can do with this grid system. But I'm a little bit curious, is there any sort of use case that you can think of where you know that this is absolutely not the right choice?
So that's a really interesting question. Certainly all grid systems have some kind of trade-offs. We have to make a lot of decisions when we implement a grid system in terms of the projection that we use, in terms of the cell shape, in terms of the cell subdivision. The ones that really jump out to my mind are obviously this hexagon hierarchy issue that we touched on earlier. And so if we do have a use case that requires very exact containment. Maybe it has parcel data or political data where we cannot, we cannot have this kind of approximate containment, but we still do need to do this truncation. Those are cases where you might not want to be using H3, or it might be a little bit more complicated for you to use H3. Another use case I can think of is related to the projection that H3 uses. H3 uses what's called the monic projection. And this does make certain trade-offs in terms of like the equal area properties. So H3 tries to be roughly equal-ish area, but it's not an equal area system. And so if you do have use cases which again do require this kind of property, it might be something where H3 is not a good fit for you.
I think sometimes it's great to talk about what a system can do, what a technology can do. For me anyway, it's really clarifying, hearing also what it's not great for. So thanks for that. So now I'm a little bit curious. So you've started a company called Unfolded. And if I go to the website, the first thing I see is pioneering advanced spatial analytics and visualization. And H3 is a big part of this. Like it's proudly displayed there on the homepage. You're using this technology. Why is it an advantage for you to use this technology with what you're doing now? What is it about spatial analytics and visualization that makes H3 just the right piece of technology?
Yes, I'm happy to chat about that. I think there are a few advantages that H3 gives us. One is I think that there's a tremendous advantage of having a geospatial analytics system that has this kind of grid system integrated throughout the entire system. When we talked earlier about the example of you need to index the data, you need to process the data, you need to visualize the data. I think that a lot of the power and benefit of having data in a discrete global grid system like this comes from this kind of integrated experience. And this is one of the things that we're hoping to build at Unfolded is we can have an experience where data on the back end, on the front end, in between is all in a consistent geospatial format. And we're able to get a lot of benefit from that because we can work with all of these different big data tools on that data and even small data tools on the data. Now, that can sound a little bit scary because you have obviously your data in these different formats already. Maybe you have zip code data if you're in the US, maybe you have it in another grid system, maybe you have it in a raster, and you're thinking, well, I still want to be able to work with these different formats. We talked a little bit earlier about the flexibility of getting data in and out of H3. And that's really one of the key things that we're able to do at Unfolded is because we have this H3 grid system, we're able to unify data spatially in a way that's very difficult with other technologies. So we're able to project data between geometries. Let's say we have in the US, a good example is maybe you have customer data in zip code format, but you have demographics data in a format you get from the US Census Bureau. They use essentially a totally different geometry. Using the H3 grid, we're able to join these. And then you can imagine that we can also bring in a raster, we can bring in a GPS track, we can bring in all these different kinds of data and unify it, join it into a single analysis that a user is doing and make it a lot easier for them to access geospatial data.
Okay, so just to clarify there, the big advantage, or at least this is what I heard, that the big advantage here is that it's all in the grid. So hexagon, everything is a hexagon when it comes down to it. So we're not looking at turning polygons into anything else or using points or whatever else. We're just converting everything into these hexagons and then treating them as independent geospatial layers and doing the analysis based on those layers.
Well, I would say that the ability to convert it back out of hexagons is also very, very important because this is the thing that allows you to do something like transform between, let's say, the example of the US Census geographies to zip codes. We're able to use the hexagon grid to do that transform in a remarkably efficient way of going from this one polygon geometry. Yeah, and from the user's perspective, we're just going from this one polygon geometry to another polygon geometry. And so they can do their analysis in a geometry that they're comfortable with and that they feel really is useful for their analysis.
Yeah, so that makes perfect sense to me. Thank you again for taking the time to sort of walk us through that. I just want to round off the conversation here with a question that I got from the good people of Twitter. And it was we got a lot of questions, but I feel like you've addressed them all during the conversation so far. But this is the one that you haven't addressed, and it's relatively simple. It's, what is your favorite adoption of the H3, excluding Uber?
So that's a difficult question because there's so many different ways to use it that I've seen just from I've seen wildfire analysis. I've seen obviously urban planning uses. So it's a tough question, and I would also just say before I answer that, because it's an open source project, we don't necessarily always get that kind of feedback of how people are using it, and so I do want to just add a little bit of a plug here of if you have a really interesting use case, if you're using it in different fields, we'd absolutely love to know at the H3 project more about what you're using it for and how you're using it. And we love getting this kind of feedback, and it's really useful for us when we're thinking about just maintaining the project, how people are using it. I think that the use case that really appealed to me the most is actually in kind of the gaming and gamification space. So I've heard a couple ideas around this. One of them is like a data provider, which I think is gamifying data collection for some of their users. And there's just something about kind of tying this to game development and things like that, which really appeals to me. And you can think of building more games on top of H3. You can think of the success of Pokemon Go and other augmented reality games. It's just really certainly a fun use case, if nothing else, to see H3 pop up as part of a game system.
Absolutely. I think anytime geospatial is integrated into games, and in the hands of normal everyday people, I think it's fantastic. I really want to thank you for your time. I want to thank you for walking us through the H3 system, explaining the do's and don'ts with it. I've really enjoyed the conversation and I really appreciate it. But before I let you go, where can the listeners go if they want to continue the conversation, if they want to find out more or reach out to you?
Absolutely. Thank you for having me. I've really enjoyed being on the podcast today. So for H3, the best place to go is h3geo.org. That's the letter H, the number 3, and then geo.org. And you can also find us on GitHub at github.com/uber/H3. For myself, you can find me on GitHub, LinkedIn, Twitter, and all those places. I'm Isaac Brodsky. And for Unfolded, you can find us at unfolded.ai.
Thanks again, Isaac. I will include all of those links in the show notes so people can find you that way as well. Hey, I really appreciate your time. Thank you so much.
Thanks again.
And that's it for another episode of the Mapscaping Podcast. My name is Daniel. It's been a pleasure being your host again this week. Just as a reminder, you are more than welcome to reach out to me on social media. If you Google host of Mapscaping Podcast, you'll find me, or look for Mapscaping on all of the channels. I would really love to hear from you. All the show notes and links and resources mentioned in the podcast episode today will be available at mapscaping.com, so please check that out. Okay, that's it from me. We'll talk again next week. Bye.